Okay, students, let us continue with this chapter. Now, next topic, quantitative aspects of electrolysis. Quantitative aspects of electrolysis. Okay, this means now we know when an electricity is passed through an electrolyte, some substance are getting deposited or liberated at their respective electrode. So we want a relationship. How much electricity is passed through, how much substance is deposited. So we want a relationship between this. How can we find? It is observed that, let us take one example. When 1 mole of Ag plus ion is reduced to silver, when one mole of silver ion is reduced to silver, when 1 farad electricity is passed through it. 1 farad electricity is passed through a solution containing a silver ion solution. It is observed that the amount of silver deposited is is exactly proportional to the quantity of electricity that is passed through is 1 farad. What do you mean by 1 farad? Let us check. 1 farad is exactly equal to the charge carried by 1 mole of electron. 1 mole of electron. We know charge of 1 electron is minus 1.6 into 10 raised to minus 19 coulomb, right? So when it's multiplied by its Avogadro number 6.022 into 10 raised to 23, that's equal to no. We know charge of 1 electron is 1.6 into 10 raised to minus 19 coulomb. The amount of substance in a 1 mole of substance, the amount of substance is always equal to Avogadro number if you take 1 mole of substance. So the amount of substance is 6.022 into 10 raised to 23 will be the number of electron if you talk about 1 mole of electron. So now the charge carried by 1 mole of electron is exactly equal to nearly 96500 coulomb. This is actually we equated into 1 farads. So 1 farad electricity means if you talk in terms of coulomb, it is 9650 almost equal to 96500 coulomb. So that was no relationship. When 1 farad electricity is passed through it, it is found that 1 mole of silver ion deposited to give 1 mole of silver. That is 1 mole of silver means 108 gram. If you talk about the atomic mass of silver is 108 gram. So when 1 farad electricity is passed through a silver ion solution, we found that 108 gram of silver is getting deposited. So let us take another example. When it is observed that for depositing 1 mole of silver, for depositing 1 mole of silver by reduction of 1 mole of Mg2 plus ion, it is required 2 farad electricity. It's required 2 farad electricity, which means when you pass 2 farad electricity, the amount of magnesium that deposited is equal to 1 mole of Mg, that is equal to how much? It is equal to nearly 24 gram. That is equal to, that is atomic mass of magnesium. Let us take another example. Talk about aluminium. If you want to deposit 1 mole of aluminium, okay, 1 mole of aluminium is required 3 farad electricity. When 3 farad electricity passes through it, so 1 mole of Al3 plus is getting reduced to give 1 mole of aluminium, which is nearly equal to, I will say, 27 gram. So from here you can understand there is some relationship is there. It is always related to the stoichiometry of the compound. Here valency of magnesium is 2, which means 2 moles of electron is required for deposition of 1 mole of magnesium. Here its valence is 1. So if you pass 1 farad electricity, it's not it's we can see the amount of substance deposited is 108 gram of silver or 1 mole of silver. So always look at the valency to understand how much substance is deposited. It's not that no same amount of electricity, same result. No. You always look at the valency of the ion which is getting reduced, and you can understand how much electron is used for the reduction. That will give you indication of how much mole of substance will be formed, how much electricity is required. So having this example, we can understand no the amount of substance deposited is always proportional to the quantity of electricity passed through it. If you pass 3 farad of electricity, you will see 1 mole of aluminium is deposited. If you pass 2 farad electricity, 1 mole of magnesium deposited. If you pass 1 farad electricity, 1 silver metal is getting deposited. So that's a very important relationship between the amount of electricity passed through an electrolyte and the substance that's get deposited. So let us do one problem related to this. Okay, the problem is how many grams of chlorine? How many grams of chlorine? How many grams of chlorine would be produced by the electrolysis of molten NaCl? Molten NaCl with a current of 1 ampere for 30 minutes. 30 minutes. So look at this problem. How many grams of chlorine would be produced by the electrolysis of molten NaCl with a current of 1 ampere for 30 minutes? So that means no 1 ampere current is passing through for 30 minutes. How many chlorine will be liberated? That's our question. We know molten NaCl is now ionized in presence of a electricity. It will split Na plus ion and Cl minus ion. Na plus ion is a cation, moves to cathode. Cl minus, which is a anion, which moves to cathode. So how much substance will deposit? When now talk about oxidation of Cl minus, half mole of Cl2 will get deposited by releasing 1 mole of electron. Okay, so which means no, if you pass 1 farad, always look at the electron, that's very easy. If you pass 1 farad of electricity, half mole of chlorine will be deposited. Half 1 farad electricity means how much coulomb? 96500 coulomb. If you pass 96500 coulomb of electricity, you will see half mole of chlorine will be deposited. Half mole of chlorine mean how much? Now it is nearly equal to 35.45 gram, which means now chlorine atomic mass is 35.5 into 2 divided by 2. So nearly equal to 35.45 gram. So which means now if you pass 1 farad electricity, or now if I talk in terms of coulomb, 96500 coulomb of electricity, you will deposit this much of substance. Now our question, if you pass current 1 ampere for 30 minutes, 1 ampere for 30 minutes means now how much electricity you have passed. We know Q is equal to IT. Q is the amount of electricity, I is the current in ampere, T is the time, how much time you pass through it. So you can find Q, which is equal to 1 into 30 minutes, always expressed in second. So 30 into 60, which is equal to 1800 coulomb. So the amount of electricity is actually passing through the electrolyte, that is sodium chloride here, is actually 1800 coulomb. Now let us find how much mass is get deposited. So let me put this value. If 1800 coulomb electricity is passing through, how much substance get deposited? That's a question. Simplify, you can write like this. If you pass 96500 coulomb, 35.45 gram of chlorine will be deposited, or no, it will be liberated. The point is now you passing only 1800 coulomb only, which means this always proportional. The mass of substance liberated or deposited always proportional to the amount of electricity. So here you are passing lesser amount of electricity, which means lesser amount of substance do get deposited. So always write if you write like this, the amount of electricity should be in the same side and the mass of substance in the same side. Now just cross multiply it. So what are you going to get? 1800 into 35.45 divided by 96500 coulomb. 96500 coulomb. You actually getting a result that is equal to, if you calculate it, you will get 0.6612 gram of chlorine will be liberated. So that's the way you can now simplify, do this calculation. Always understand only one point. The amount of substance get deposited or liberated always proportional to the quantity of electricity passed through it. When you stop electricity, the substance formation always stops. So that is one problem. You all know sometime will be asked. So you practice like this. So let us do one more problem. This time, how long does a current of 1.5 ampere needed to pass through a solution to deposit 2 gram of aluminium. Okay, how long does a current of 1.5 ampere need to pass through which solution is actually aluminium sulfate, Al2SO4 thrice aluminium sulfate solution to deposit 2 gram of aluminium. So here you have to understand the electrolyte is aluminium sulfate. So now the cation will be Al3 plus, that's get attracted to the cathode, and now anion generally in the case of sulfate it will be oxygen will be released. So that we already discussed in the previous class. So here the question is how long a current should pass through for 1 ampere of current needed to pass through a solution to deposit 2 gram of aluminium. If you want to deposit 2 gram of aluminium, how much current is required? So let us do the calculation. We know Al3 plus 3 electron gives Al. So this is the reduction reaction that takes place at the cathode. Which means if you pass 3 farad electricity, the amount of aluminium deposit will be nearly equal to 27 gram of aluminium, which is the atomic mass of aluminium. You talk about 1 mole of aluminium, it is 27 gram. 3 farad electricity will deposit 27 gram. So 3 farad electricity means how much coulomb? It is 3 into 96500 coulomb, which is equal to 27 gram. Now if you want to deposit 2 gram, how much coulomb of electricity is required? Just write the mass and the quantity of electricity on the same side, just cross multiply it. What are you going to get? 3 into 96500 into 2 divided by 27. Now if you calculate it, you will get, which is equal to 2124 coulomb. Okay, so you get the amount of electricity. Now what's the question? How much current? We know Q is equal to IT, right? Q is equal to IT. Here now I is given, current is given, and we have the value 21444. That's the quantity of electricity, and current is 1.5 ampere. How long? Which means you have to find the time. How can you find the time? 21444 divided by 1.5. If you do that calculation, you will get 1296 seconds. So you have to pass an electricity of electric current of 1.5 ampere for 1296 seconds for depositing 2 gram of aluminium. Okay, so that's the way you have to practice. So let us do one more problem. How much electricity will be required for each of the following? How much electricity is required for each of the following? Here, talk about reduction reaction from, talk about now reduction from 1 mole of MnO4 minus 1 mole of MnO4 minus 2 Mn2 plus. Okay, that's the first one. So here now you have to understand MnO4 minus is a permanganate ion. Oxygen is no more electronegative, so oxidation state is minus 2. 4 into minus 2 is equal to minus 8, which means the whole charge, if you want to get minus 1, means no manganese in the plus 7 oxidation state. So MnO4 is getting reduced to Mn2 plus by now 5 moles of electron are reduced is required for the reduction of permanganate ion to manganese ion, Mn2 plus ion. So now you can understand for this reduction to carry out from now 1 mole of MnO4 minus to 1 mole of Mn2 plus, you require now 5 Faraday electricity. So 5 into, look at this number of electron, 96500 coulomb electricity is required for the deposit. So if you calculate it, you will get 482,500 coulomb. Similarly, for the deposition of 1 mole of silver, like 1 Faraday electricity is required. Okay, you can calculate it. 1 Faraday is equal to 96500 coulomb. Now this time the question is now actually 0.25 mole. Okay, 0.25 mole. Just the difference is there. 0.25 mole now is getting reduced to how much? If now we know 1 mole of silver. 1 mole of silver will silver ion get deposit will reduce to give 1 mole of silver. So here now 0.25 mole of silver ion means now you are always going to get 0.25 mole of Ag. This is always proportional. So the amount of electricity is now required will be 0.25 farads. So if you calculate it, you will get 0.25 into 96500 coulomb. So if you calculate it, you will get 24125 coulomb. Okay. If 1 mole of Ag plus ion reduced to 1 mole of Ag, 1 mole of electron is required. Similarly, 0.245 mole of Ag plus to get 0.25 mole of Ag, 0.25 Faraday electricity is required. Okay, that's the way you can calculate it. Okay, similarly, such problems are there. Now you have to practice more questions. Okay, let us move to the next session. Next is Faraday's law of electrolysis. Faraday's law of electrolysis. There are first and second law is there. What is first law of Faraday's law? First law of Faraday's law of electrolysis. First law suggests that, no, as we discussed before, the amount of substance deposited or liberated in a respective electrode is always proportional to the quantity of electricity passed through it. So let W is the mass of substance deposited, that always proportional to Q. We know Q is equal to IT. So W is proportional to IT. You can write like this. The proportionality sign is multiplied by a constant that I call set. So W is equal to set IT. That is Faraday's first law. The amount of substance gets deposited or liberated in an electrode is always proportional to the quantity of electricity passed through it. This is the first law of electrolysis. Okay. Here W is the mass of substance deposited. Z is the electrochemical equivalent. Electrochemical equivalent. And I is the current in ampere, T is the time in seconds, how long it's passed through. Electrochemical equivalent we can define. No, it's nothing but if, imagine if I is equal to 1 ampere, T is equal to 1 seconds, then we can get W is equal to sets. So electrochemical equivalent is the mass of substance deposited when 1 ampere current is passed through for 1 second. Electrochemical equivalent set is the mass of substance gets deposited when 1 ampere of current passed through 1 second. So that is, that's the way you can define electrochemical equivalence. So we found an equation, W is equal to ZIT. That's from the first law of electrolysis. Now, what is second law of electrolysis? second law of electrolysis. Now you imagine if same amount of electricity is passed through two different electrolytes. Now is there any relationship? We talking about passing same amount of electricity passing through two different electrolytes. The mass of the substance deposited have a relationship? Yes. It is found that WA divided by WB is always equal to EA divided by EB, where EA and EB are the equal mass of the respective substance. EA is the equivalent mass of the element or substance, we can say. So let us know how to find a equivalent mass. No, if we know the atomic mass, then the equivalent mass now for the species which undergo oxidation or reduction can be easily found. Atomic mass divided by number of electron that get reduced or number of electron that is released during the oxidation. So we can say no, the number of moles of electron reduced or oxidized, depending on the substances undergo oxidation or reduction, you can find it. So let us take one example. The two solutions that pass through is copper sulfate solution and silver nitrate solution. Imagine the same amount of electricity is passed through these two different electrolytes. One is copper sulfate solution, one is silver nitrate solution. How much substance do get deposited? Now we can find out first, we know copper 2 plus ion get reduced to copper and silver ion is get reduced to silver. Okay, so let us try to find the equivalent mass of copper. Here now 2 moles of electrons are used for the reduction from copper 2 plus to copper. So the equivalent mass of copper, which is equal to copper having atomic mass nearly 63 point, let me check, 63.54. 63.54, that's that is the atomic mass. Yes, equivalent mass of copper can be found by atomic mass 63.54 divided by number of electron reduced is 2. So if you divide it, you will get 31.77 grams. That is the equivalent mass expressed in gram. Okay. So what about silver? You can see 1 mole of electron is there, which means now atomic mass and equivalent mass of silver is equal, which is nearly equal to, for silver the equivalent mass equal to 108 gram. Nearly that is the now equal to atomic mass. So now imagine if same amount of electricity is passed through both silver nitrate solution as well as the copper sulfate solution, the mass of substance that get deposited, let it be WAG divided by WCU. How can you write? The mass of silver that get deposited divided by mass of copper that get deposited is proportional to the equivalent mass. Equivalent mass of silver is 108. Equivalent mass of copper is 31.77 gram. So that's the way you can find a relationship between these two. So how can you define second law of electrolysis? If same amount of electricity is passed through two different electrolytes, the mass of substance deposited the mass of substance deposited is proportional to the equivalent mass of the elements. Okay, that's another relationship. Okay. Okay, now we have to find a relationship between the electrochemical equivalent and the uh, equivalent weight. Let us try to find. We know when 1 farad electricity is passed through 1 farad electricity is passed through any substance. If 1 farad electricity is passed through any substance, the amount of substance that gets deposited is always proportional to the equivalent mass of the substance. The equivalent mass of the substance. Okay, this is something that you observe. If you pass 1 farad electricity through any electrolyte, the amount of substance that deposited, that's always equal to equal mass of the substance. So we have an equation W is equal to ZIT from the Faraday's first law. We have an equation where I is the current and T is the time of how long it is passed through. So if you know, you substitute Q is equal to IT. We know Q is equal to IT, right? So imagine 96500 coulomb electricity is passed through. 96500 coulomb is nothing but 1 farad. So W I can put set into 96500. Okay, I put now, I imagine 1 farad electricity is passed through the solution. So I put IT is equal to Q, which is equal to 96500 coulomb. Now, it is observed that when you pass 1 farad electricity, or when you pass 9650 coulomb of electricity, the mass of substance deposited is always equal to equivalent mass. So I can replace W by E. E is equal to Z into 96500. So how can you find a relation between these two? Z is equal to E by 96500. So that's the relation between the electrochemical equivalent and equivalent mass. If you know the equivalent mass of the substance, you divide by 1 farad electricity, that is 96500 coulomb. You're going to get electrochemical equivalence. Okay. Now, if a question asks, to find the amount of substance that deposited, you can still find, using the Faraday's equation, Faraday's first law equation, W is equal to ZIT. So using that equation also you can find it. It's up to you how you want to find. So let us do one problem. Okay, the same problem that we done. The how many grams of chlorine? How many grams of chlorine produced by the electrolysis of produced by the electrolysis of produced by the electrolysis of molten NaCl, molten NaCl, molten NaCl with a current of with a current of 1 ampere for 30 minutes. So this is the same problem that we done previously, no, without using Faraday's equation. Now let us do the same problem with Faraday's equation. W is equal to ZID. Okay. Now we can substitute Z is equal to E by 96500. We know the equivalent mass of chlorine, that is equal to 35.45 divided by 96500 coulomb. If you substitute that value, you will get Z. You have the value of I, which is 1 ampere, and we have the value of T, which is 30 seconds. So which should be converted into, sorry, 30 minutes you should convert into 30 seconds. So W, mass of substance deposit, is equal to 35.45 divided by 96500. Where is the equivalent mass of chlorine? Okay, equivalent mass of chlorine is equal to 35.45 into 1 ampere into 30 into 60. For converting into seconds, we have to multiply 30 into 60. So the answer again is going to get the same answer, 0.6612 gram. So such problems are there, 132. Okay, 132. If you do calculation, it will be this. So if you do that calculation, you will get an answer like this. So this is the way we can still find the mass of substance that deposited is always proportional to the quantity of current into time into electrochemical equivalent. That is the Faraday's first law of electrolysis. Okay, so please do more problem like this. It is more problems you get, that will be nice. Remember, we found a relationship between Z and E. Z is equal to E by 96500 coulomb. The another important point that we learn now, if you pass 1 farad electricity through any electrolyte, irrespective the nature of electrolyte, you pass 1 farad electricity, the amount of substance deposited will be always equal to the equivalent mass of the substance. Okay, so do such similar problems. Okay, so let us continue in the next class. Okay, thanks for listening.